Unfreeze. All right, so let's go over the warm-up. So the first... Oh, that's interesting. Okay, so if f prime is 2x, well, what function has a derivative of 2x? It'd be x squared. I see some extra credit on some boards, which is fantastic. There are obviously students who have taken calculus before in this room. So first period, no one knew. So that's interesting that like everyone who took calculus before ended up in second period. So anyway, f of x is x squared. Let's just go with that right now. All right, so this is for part A. All right, so for part B, all right, what function has a derivative of x is 1/2 x squared, which everybody got. Well done. Yep, okay. Part C. So what function has a derivative of x squared? Well, we know it's going to be an x cubed, but we can't have a 3 in front, so we got to do 1/3 x cubed. There's a whole joke about 1/3 x cubed that I will tell you later. All right. The next one I thought would be tough, but everybody got it. So well done. The derivative, or the function whose derivative is x to the negative second, is negative x to the negative first. So our f would be negative x to the negative first. And then the derivative, or the function whose derivative is x to the negative third, well, we know it's going to be an x to the negative second, but we can't have a negative 2 in front, so to get rid of that, we have a negative 1/2 x to the negative second. All right, so my question to you, which many of you already know the answer to, for part A, is this the only function whose derivative is 2x?
No.
It's, name another one.
X squared plus 1 million.
X squared plus 1 million?
Yeah.
What about x squared plus 2, right? Yeah, very good. They're both correct. I can think of at least 2 more. Right? All right. So because there are infinitely many functions that have a derivative of 2x, but they're all the same, just the only difference is we don't know what constant was added, right? Was there a constant there? Because all constants go to 0 when you differentiate. So if there's some mystery constant, how do we write this mystery constant? We represent it with a plus c. So this plus c represents whatever unknown constant might have been added to this original function that then went to 0 when we took the derivative. So if you see these plus c's on some of the board, one board went to plus n. I don't know why you guys chose plus n, but I will tell you, don't do plus n on the AP exam. Go with tradition, which is plus c. So anyway, but it's correct. So, you know, you did fine. Yeah, so anyway, so this plus c we're going to get into a little bit deeper today. Represents whatever unknown constant happened to be added to your function. Okay, so I'm going to show you the slide to tell you what section we're on, and then we're going to pause the video for a few minutes. So we are starting today, even though we are doing chapter 5, the first 2 days we're going to be still in chapter 4. So we're going to spend 2 days on section 4.9. 4.9 is about antiderivatives. All right, I'm going to pause the video. All right. Antiderivatives. Okay, so antiderivatives, a function f, big F, is called an antiderivative of little f if the derivative of big F equals little f. Big F is not accepted notation for an antiderivative, but it is often used. If you have in one problem a big F and a little f, usually that means big F is the antiderivative of little f, but you can't assume it. They have to specify something like this to say, look, big F prime equals little f, so big F is the antiderivative of little f. Okay. Doing an antiderivative, finding an antiderivative is really like undifferentiating. I kind of like the name, antiderivative. You're undoing a derivative. Your book does not teach this notation until section 5.4. So for antiderivatives. We do this notation for other stuff, but not specifically for antiderivatives until section 5.4. I'm teaching it to you now, and I want you to learn it and get comfortable with it for a couple of reasons. One is there's no cute notation for an antiderivative. Like there's no, hey, like if I have the derivative of f, I can write f prime. There's no f anti-prime. There's no such thing. Like there's no notation for an antiderivative. The only notation that you'll see that's common besides this is calling it big F and then specifying that big F prime equals little f, which is kind of a pain in the butt. So most often, the way that we use our notation for antiderivatives is this way, which is this integral symbol. So the symbol right here, which is called an integral. So just so you know, there's two branches of calculus. You have differential calculus, you have integral calculus. Differential is all derivatives. Integral is basically antiderivatives, right? We are now starting into integral calculus, and we're going to start with the integral symbol. The stuff inside the integral symbol is called the integrand. So I don't know if you've ever done, like if you know your division problem, like if you have a division symbol, the stuff inside the division symbol is called the dividend, right? If you have a radical symbol, like a root, the stuff inside the radical symbol is called the radicand, right? The stuff inside the integral symbol is called the integrand. All right. This stuff, well, that's the antiderivative. And your C, that is a part of your antiderivative, has its own name. It's called the constant of integration. The constant of integration. There are two types of integrals, just like there are two types of derivatives. Way back when you were doing derivatives with limits, you learned general derivatives with f prime of x, and you learned specific derivatives like f prime of 3. So integrals, the same thing. You have indefinite integrals, which are antiderivatives, and then you have definite integrals, which involve numbers. So an antiderivative and an indefinite integral are basically synonyms. They're the same thing. So often if you hear someone say, find the integral of this function, it's the exact same thing as find the antiderivative of this function. They're basically synonymous. One last little note, and then we'll move on, this dx right here. So dx has a lot of meaning embedded in it, but for you guys right now, all you need to think of it as is just this thing that tells you what the variable is. Just like when you first learned derivatives and we called it dy dx, the dx is just telling you we're doing the derivative of y with respect to x. It's telling you your independent variable, your input variable. Same thing here. That dx just identifies the input variable. Now it does a lot more, but that will be later on. That we'll learn what else it does. Same thing like when you did your dy dx. That dx does a whole bunch more stuff, but some of which you won't learn until next year when you all take Calc 3. All right, everyone have the notation written down. All right. Okay. When you have an antiderivative, so this is the graph of 1/3 x cubed. 1/3 x cubed is the antiderivative of x squared. when we have the antiderivative, so I'm just going to rewrite it. The antiderivative of x squared dx is 1/3 x cubed plus c. So if I were to graph the antiderivative, I would have 1/3 x cubed, but I have it with some unknown constant, right? Now, if I filled in like every possible real number for the unknown constant, then I just get the solid graph, right? It'd just be nothing but solid ink. So traditionally, what we do is if we want to graph what's called the family of antiderivatives, we just put in integers for the constant. Like, hey, here's 1/3 x cubed plus 0, 1/3 x cubed plus 1, 1/3 x cubed plus 2, right? And it's just a bunch, it's just kind of showing what the antiderivative looks like for a bunch of different values of c. So you can see kind of, in general, what the antiderivative gives you. So remember the plus c is just a vertical shift up and down, right? So it's really just the same function shifted up and down. Okay, now I have an assignment for you guys. Before you start, I'm going to add something to it. So find the most general antiderivative for each of the following. So in your groups, I want you guys to see if you can figure out the antiderivative of sine x, the antiderivative of 1/x, and the antiderivative of x to the n if n is not -1. So for part B, this is x to the negative first. For part C, this is x to a power, all other powers except -1. This is going to be kind of like a rule. This is going to generate kind of a power rule for antiderivatives. This guy, I want you to think, when you're figuring it out, think for each of these, what function has this as its derivative? That's what you should be thinking about when you're thinking about all these, okay? What function has this as its derivative? That would be the antiderivative. The other thing I want you to do while you're working on these is I want you to take 30 seconds and introduce yourselves to your group mates. Make sure you all know each other's names, maybe, chat for a minute before you start working on the problem. All right, I'm going to give you about 4 minutes. Go. So a little hint for, little hint for part C. So, which you've already done today. So today you said the antiderivative of 2x was x squared. You said the antiderivative of x was 1/2 x squared. You said the antiderivative of x squared was 1/3 x cubed. You said the antiderivative of x to the negative second was negative x to the negative first. You said the antiderivative of x to the negative third was negative 1/2 x to the negative second. You did all of those for your warm-up. See if you can look at this and figure out a pattern to find it for a generic case of x to the n. So take another minute, 1 more minute, see if you can figure out a generic case. First one first for part A. So the integral or the antiderivative of sine x, what function has a derivative of sine x? Negative cosine x, right? Because the derivative of cosine is negative sine, so in order to make it positive, we have to do negative cosine, right? So the antiderivative of sine is negative cosine. Now, sine and cosine, we're not going to do all the trig functions today. We're going to get into those on Monday. But today we just got sine and cosine. Sine and cosine, even though they're the easiest, because they're always just switched between each other, they're also the most missed because of the negatives. So it's so easy to get confused. When you are taking tests from now on, every test can have a mix of both derivatives and antiderivatives. And it's so easy to get them mixed up in your head. Derivative of sine is cosine. Derivative of cosine is negative sine. Antiderivative of sine is negative cosine. Antiderivative of cosine is sine. To get them all mixed up with the negatives. So how do you know, are there memory tricks? So for me, whenever you're doing a derivative and the trig function starts with a c, the answer is negative, right? That's always been true. The derivative of a trig function that starts with a c is negative. For antiderivatives, it's if the answer starts with a C. So if the answer starts with a C, it's negative. Why? Because if you were to go backwards, that would be your first function, right? And it would start with a C. So for derivatives, if the function starts with a C, the answer is negative. For antiderivatives, if the answer starts with a C, it's negative. Okay? Little memory help. Hopefully that will help you somewhat. Anyway. All right. Part B. What function has a derivative? Luke, what function has a derivative of 1 over x? ln x plus c, right? Always plus c, plus c. By the way, if you want to lose a whole bunch of points on your test, right? How can you do it? Forget to write all your plus c's, right?
Wait, what?
Every time you don't write a plus c, you lose a point. Yeah. Okay. I have some students who every time they sit down to a quiz or a test, whenever every single problem where they see an integral, they put a plus c before they even start. Like they just sit there and fill plus c and for the whole test, and then go back and work all the problems. Anyway, I don't expect you to do that, but please get in the habit of always writing a plus c with every antiderivative. All right, this is close, but it's not complete. So 1 over x looks like this. This is y equals 1 over x. What's the domain of that function? All reals except 0, right? All reals except 0. Natural log x looks like that. What's the domain of that function? Right, x greater than 0, right? So the derivative of this doesn't give us this. Technically it does, but you have to accommodate the whole domain when you're going this way. So really either way. But so when we went this way, this gave us extra. Extra's okay, but not enough is not good. So we have to have antiderivative for every x value in the domain of the function. So how do we end up accommodating the full domain of this function? Keegan, was that you? Way to go. Yeah. All right, how do we do it? We want this, pretend those are symmetric. We want ln on both sides, which means you have to put an absolute value under x. So the integral of 1 over x is natural log of the absolute value of x. All right. Part C is a formula. I like to think of this formula as, go away from mine, there we go, as the socks, shoes, shoes, socks formula. Because when you get dressed, you put on your socks, and then you put on your shoes, right? Okay. Yeah. So when you get undressed, you have to take off the shoes first before you can take off the socks. Are we all okay with that, right? Okay. So when you do a derivative, you put the exponent out front and then reduce it by 1, right? You multiply and then reduce. To undo that, you not only have to do the opposite operations, you have to do them in reverse order. So when you're doing a derivative, you multiply and then reduce. When you're doing an antiderivative, you raise the exponent and then divide. It's opposite operation and opposite order. So, Suhair, what's the antiderivative of x to the n?
1 over n plus 1 times x raised to n plus 2.
So you raise the exponent by 1 and then divide by the new exponent. Raise the exponent and then divide. So, for example, if I asked you, hey, what's the integral of x to the 7th? 1/8 x to the 8th plus c. These will get quick. They really will. You'll get, so it's just like derivatives, right? If I said, hey, what's the derivative of x cubed? You could say 3x squared in 2 seconds, right? You hardly even have to think about it anymore. Integrals will get to be that the same way. You'll get that comfortable. You just, for me mentally, I add 1 to the exponent, so I think, all right, I want x to the 8th, and then I write the 1/8 and then put the x to the 8th. I don't do this first and then I was like, I think this first, but I do my dividing first. Anyway, okay. So, are we? Oh, yes, Jennifer.
So if you had like 3x squared or whatever, as like, and you find the integral of that,
Yeah.
3 on top, and then
Here, let me
x plus
make
1
this wide.
x
Woo,
and
that's
x plus
really
1.
wide. Okay. So, for example, if I had the integral of 3x squared, raise the power by 1, so you have an x cubed, right? And then you're going to divide by 3.
Yeah.
Right?
Oh, yeah.
Right? Raise the power by 1, divide by 3. 3 divided by 3 is 1.
But if you had like any numbers, so would that go into the numerator of like the little 1?
If I had like 7x squared,
Yeah.
then you'd have 7/3 x cubed plus c.
Yeah.
Right? Raise by 1, divide by the number. Coefficients always just come along, forwards and backwards, right? So, okay. So, that being said, do not spend time writing all these down. Please, do not. So, this is in your book. It's a table of anti-differentiation formulas. It's in the PDF. You can always look at the PDF if you want. We're going to walk through these like in notes anyway. You'll eventually have all these in your notes. But this is there just for reference. What I want you to see is most of these aren't that like, whoa, amazing. It's really just derivatives backwards, right? So they're saying, hey, the antiderivative of secant squared is tangent. Whoa, because the derivative of tangent is secant squared, right? And all they're doing is like giving you derivatives backwards. So anyway, so this is there for you to refer to if you want to. Moving on. These are where I have fun. So we're going to do 2 of these kind of like in groups together, and then we'll start hitting the whiteboards again. So if f prime equals 8x cubed plus 4x minus 5, find f given that f of 1 equals -3. Now I don't want you to look at this yet. All I want you to do is take 30 seconds and write the antiderivative of f prime. So the antiderivative of f prime would be f. So I want you to write f. See if you can figure out f. Once you get it, compare with your group members, make sure you all match. You do not need a phone for this. Tarun, how are you? What'd you guys get for your f of x?
2x to the 4th plus 2x squared plus c.
The derivative of -5 is 0. We're not doing the derivative of -5. We're doing the antiderivative. The derivative of what function equals -5? -5x. So be careful. When you hit a constant and you're going backwards, you're not going to 0, you're going the other way. You're adding x's, not getting rid of them. So the antiderivative of -5 is -5x. Everyone got that? Good. All right. Now that we all agree on our f, they've given us this information. They've told us that f of -1 equals 3. How does that help us?
Also,
you can find C. So everyone take a minute and see if you can find C. Wow. My neighbors have already put up their lights. So. All right, what did you guys find for C? -6? Everybody? Yes? All right, let's see. F of -1 equals 2 plus 2 plus 5 plus C. And this has to equal 3. So you get 9 plus C equals 3. So C equals -6. This is not the answer to the question. The answer to the question is the full f of x. So take the 2 seconds and rewrite your function with the correct C. Add it in. And now we have a true antiderivative of this function. Yes, all right.
Do we have to write the integral of 8x cubed plus 4x minus 5 dx equals that?
No, but you could. But personally, if they've labeled this f prime, then the antiderivative, you can just call it f, because that is the antiderivative.
It's only if they label it
if they just say find the antiderivative of this and they don't give it an, or if they call it f and say find the antiderivative, then there's no like lower thing than f. So just so you know, if it's called f, you don't have to rewrite the whole function. You can just write that, right? Like if they call it f, you can write f because they're equivalent, right? So anyway. Okay, one more that I want you guys to try for a couple minutes in your groups. So now they're giving us f double prime. Then they give you information about f prime. And then they give you information about f. Little warning, you will have an unknown constant for f prime and another unknown constant for f. Deal with the f prime first. Once you figure it all out, then go down to the f. I'm going to pause. So, Anisha. Hang on, I gotta move this. All right. What'd you get for f prime?
6x squared minus 4x plus c.
Beautiful. Okay. From here, if you're given information about f prime, use it, right? So f prime of 1, which equals 6 minus 4 plus c, has to equal 5. So 2 plus c equals 5, so what is c? 3. So now rewrite your f prime. So you get 6x squared minus 4x plus 3. All right. Anthony.
Yes.
How are you?
Good, how are you?
I'm doing great. All right, so this is my f prime. Can you tell me f?
2x cubed minus 2x squared plus 3x plus c.
Fantastic. All right, here we get into a little snag, which is we can't call this unknown constant c unless it also happens to be 3. Because we've already said that c equals 3, So, yes, so there are two ways you can go. You can either just call it K, right? Give it a new letter, call it Q, call it sigma, whatever you want to call it. Or you can just throw on some subscripts, right? This could be C sub 1, and this could be C sub 2. That's fine. So either you can use subscripts, or you can just pick a new letter. All right, so f of 1, which is 2 minus 2 plus 3 plus our second unknown constant, has to equal negative 2. So C sub 2 equals negative 5. So our final function is 2x cubed minus 2x squared plus 3x minus 5. How many of you guys got that whole thing? Way to go. Fantastic. Okay. All right. Are we ready to move on? Moving on. All right, we're going to do a little bit of PVA, a little bit of motion. College Board loves motion problems, and they love to start you with velocity because the derivative of velocity is acceleration, and the antiderivative of velocity is position. So they can test you on your derivatives and your integrals like all in one problem, right? So they love to do PVA problems because you have to do all the math you've learned during the year in one wonderful problem, right? So we're going to have some PVA. It never goes away. You use it all year long. So anyway. All right. So we're given a velocity function of sine minus cosine. Find the position function s if you know that s of 0 equals 0. So it's what you've been doing. You're going to be finding the antiderivative because if the derivative position is velocity, then the antiderivative velocity is position, right? So in your groups, take a minute and just work on this one. We're going to go through this, and then we have a board problem. Casper.
Hey, what's up?
Not much. What's up with you?
I forgot to ask it once I got done.
So can you tell me what the antiderivative of sine minus cosine is?
Yeah, negative cosine t minus sine t plus c.
Beautiful. Everyone get that? Any questions on the positives or negatives? No. All right. Firm answer from Faith. All right. So now we got to solve for c. So s of 0 equals negative cosine 0 minus sine 0 plus c, and this equals 0. So c is 0. Done, right? Piece of cake. Right?
No.
Sure about
No.
Another no.
Another no. So what's the cosine of 0?
1.
1. So this is negative 1. What's the sine of 0? 0. Plus c equals 0, so our c is 1. So watch out. They love to do problems where you plug in a 0 into cosine, and so it's a trap, right? It's not 0, it's 1. All right, so s of t equals negative cosine t minus sine t plus 1. All right, how are we feeling about these? Okay. All right, let's see what you can do on your whiteboards. I have given you acceleration and no information about velocity. So good luck finding your position. All right, so if our acceleration is 10 sine plus 3 cosine, so velocity is the antiderivative of acceleration. What is the antiderivative of sine? Negative cosine, right? So this is negative 10 cosine t. Remember, coefficients just always come along for the ride, forwards and backwards. They're always there. All right. What is the antiderivative of cosine? Sine. Cosine now finally gets a positive answer, right? So you end up with plus 3 sine t plus c. All right. We have no information about the velocity, so we just got to keep going. So I see some different interpretations of, whoops, I'm writing it A, and it should be S, of what to do with the C. So my question to you, well, let's walk through. What's the antiderivative of cosine? Sine. So this should be negative 10 sine What's the antiderivative sign? Negative cosine. So this is negative 3 cosine. All right, c is a constant. What's the antiderivative of 5? 5x. What's the antiderivative of c?
CT.
Cx, but in this case ct, because our variable is c. ct plus, we still need another unknown constant.
K.
Every antiderivative has an, we'll call it k, okay, has an unknown constant. All right, now let's plug in and see what we get. S of 0 equals 0 minus 3 plus 0 plus k, and it equals 0, so our k is 3. Now, I personally, I am a very methodical when I do my math problems, even though, like, I have messy writing, but I'm still, like, I write each step. I always do. So I rewrite my S of t with my unknown constant put in. Then I plug in the other information that's all for the other unknown constant. So the other information said that S of 2 pi equals 12. So S of 2 pi equals, so what's the sine of 2 pi? 0. What's the cosine of 2 pi? 1. So you end up with negative 3 plus c times 2 pi, or 2 pi c, plus 3 equals 12. The negative 3 and 3 are gone, so c, okay, no, c, this is c. Yeah, I found it, okay. C equals 12 over 2 pi, or 6 over pi. So our final S, oh, and there's the bell, is negative 10 sine t minus 6 cosine t plus 6 over pi t plus 3. All right, and we are done. All right.